let's see. I'm going to check us out on YouTube over here. See if we are indeed live. We are live. Let's see here. I'm going to do that so that I can see the comments coming in. All right, there we are. I can see us on YouTube. Perfect. Okay, so we are going. It says we have an excellent connection. Whoa, hey, there's Tom Dimitrovich immediately saying, "Hey guys, break a leg." Tom, good to see you, my friend. Thanks for stopping by. Looking forward to it. So, my man Peter Graser will try to do as good a job as Peter and Tom did. That might be tough though. And that little noise there just reminded me to mute Facebook. Perfect. All right, Logan Millington, NEC consultant out of the New York area. Logan, good to see you. So we're starting to pop some people in here. I got the notice on my phone that we're going. Hello from Panama. Peter, you are officially international, buddy. What do you think of that?
I love Panama.
Yeah?
Yo amo.
I've never
Yo
been
amo
to...
Panama. Lo conozco mucho.
Hey, can you guys out there, can you guys hear Peter okay if he starts talking? It's now we're just going to have to make him start talking. All right, Jorge says he can hear you. And as you might have guessed, Jorge Gutierrez is the person from Panama. So we got people.
All right. All right.
Just give it a couple of minutes here. Let some people pop in. It's 6:01, so maybe get started here in 2 minutes. We got 31 watching already, so that's good. Chris Foland is in the house out of Colorado. He says he would like to see some myths destroyed. And Chris, I would too. I am all about getting the correct information, you know. And what I've found is when it comes to new products or new technologies, and especially something that really shifts a person's paradigm, people will just refuse to understand it and they'll hate it. You know, and people will just make a decision that they're never going to want to learn about it and they're never going to embrace it. And I don't understand that, you know, personally, but here's the thing, even if you decide that you're never going to use copper-clad aluminum, this stuff is here. It's not coming, it's here, and we all need to know how to work with it when we deal with it. You know, even if you don't want to install it, you're going to run into it in an installation. I have somebody whose beautiful name I can't pronounce, but he says hello from Palestine. All right. So we are definitely of the international flavor here. Good, good, good. So thanks everybody for stopping by. Really excited to be doing this with you guys. As I mentioned, we're talking to a friend of mine named Peter Graser from Graser. I keep on wanting to say Graser. Peter Graser from Copperweld, and I'll let him introduce himself here in just 1 second. But really honored to have Peter with us, because I don't think there's anybody in the country that knows copper-clad aluminum better than Peter. I can't possibly think that there would be somebody. And that might even be a statement of fact if we're talking internationally. You know, I don't know that there's really... How does it feel, Peter, to think that you probably know more about this product than anybody else on the entire planet? That's kind of a cool thing.
Well, that's very gracious, Ryan. I can tell you something, and this is indeed fact. I am standing on the shoulders of giants, and you know, what I know about copper-clad aluminum is directly derived from people who taught me.
Yeah.
And but one thing to keep in mind, and this is surely fact. There is a rich library of knowledge about copper-clad aluminum, and we hope to share some of that knowledge today with your listeners.
Well, and I think a lot of people are thirsty for that knowledge. You know, Like I said, I think we can convince people that it's not a scary product. It might be relatively new. I mean, it's certainly newer than copper and newer than aluminum, but it's got a 50-year track record. But I think a lot of people haven't seen it before, and I think a lot of people are excited to see it, and a lot of people need to know how to work with it. So, Peter, why don't you go ahead and introduce yourself? Tell us a little bit about yourself, if you would.
Sure, sure. Thank you, Ryan. Um, Welcome to my home. This is this is for me a great honor to be with Ryan this evening. It's 6 o'clock Eastern, and end of the day, we're all thinking philosophically, right? So why not talk about copper-clad aluminum?
Absolutely.
Why not? I am the president of the American Bimetallic Association. It is a relatively new association that was created by like-minded souls in our industry to basically spread the word, spread our knowledge base, as I referenced earlier. I'm also the VP of building wire, codes and standards, testing, and environmental optimization for copper weld bimetallics. A company that has a rich history in itself. We were founded in Glassport, Pennsylvania in 1915. We have a long history in grounding, electrical grounding, and we invented the copper weld ground rod back then, so we are a very conservative company that's interested in public safety, without question. And I'm also a voting member of Code Making Panel 6 of the NEC, which deals with a good chunk of Chapter 3, not all of it, 310, 311. We do all the wiring methods, and we do a bit of Chapter 4.
You guys have
400
what, cords and fixture wire, and then you've also got all the cable wiring methods: AC cable, MC cable,
That's right.
UF cable, NM cable. Yep.
Yeah.
And while we're talking about that, let's go ahead and do our little disclaimer thing. Okay, I'm on Code Making Panel 17. You're on Panel 6. We're both on UL Standard Technical Panels. Neither of us speak on behalf of them. I don't speak on the behalf of anybody. I can't imagine anybody that would let me speak on their behalf, so I don't do it. Peter, you're qualified to speak on behalf of other people, so I don't know if you're speaking on the behalf of Copperweld, but you're not speaking on the behalf of NFPA or UL, and all opinions are your own, and the whole thing, right?
That is completely true.
Can't forget
I
that
refuse to speak for NFPA, and if I mistakenly appear that I seem to be, that is not the intention.
part. Perfect.
UL as well. Yeah, it's when you're so into this industry, like you and I, Ryan, you gravitate to these code making panels. They kind of pull you in, right?
Right.
And whether you like it or not.
Yeah,
But
absolutely.
I also sit on the SDP Standard Technical Panel for UL 486-0486, which is electrical connections and whatnot, and also 0719, which is a non-metallic sheath cable.
Oh, nice.
And UF.
Okay.
Yeah. So that's about it for my credentials that pertain to. Now, I'm also a heck of a dishwasher. I know how to mow the lawn.
Nice.
I'm credentialed there.
Yeah, for somebody, I mean, because this is pretty much what I do for a living. I teach seminars, and then I write books and different things. But, for somebody that gets paid to speak, talking about myself is always the hardest part. I hate introducing myself because the whole thing just feels like you're patting yourself on the back, and it's just like, can we just talk about the technical stuff? So let's talk about the technical stuff, man. Tell me about copper-clad aluminum. I'm excited for this.
Well, good. I thought that I'd cover 5 points today. Keep it at a high level. I mean, this is the afternoon. Want to make this enjoyable as much as possible. Don't want to dive into too many technical details, but we're gonna certainly treat the things that need to be treated, and we're going to talk about history. We're going to talk about the manufacturing process and how copper-clad aluminum is made. We're going to talk about the difference between copper-clad aluminum, CCA, and aluminum and copper. How does the metal differ from those other two metals? And we're going to talk about terminations from a very high level. The science behind what makes a good termination and what doesn't. What elements have to be there to make a good termination, a good safe termination, right? And then finally, I want to talk about some testing that was done over roughly the year 2020, over a span of about 8 months, from the Bimetallics Task Group, which was created by an act of the Standards Council, the NFPA Standards Council, and independent task group, and put under the the authority of the correlating committee of the NEC. I don't know if authority is the right word, but let's just say that it was overseen.
Yeah, the oversight.
Our chair was is a member of the correlating committee, and we conducted some testing. It was essentially created by the NFPA Standards Council after the 2020 code cycle, because there were so many questions about CCA and the fact that it was coming back, and so the NFPA thought it wise to create essentially what it is a study group, right? And so talk a little bit about that testing and the results there.
So really quick, we've got a lot of people that are online watching us, and hello everybody, and thank you. In fact, Brian Rock, probably both of a friend of both of us, just popped in. Don Gagne, it looks like Chuck Mello is here. Chuck knows a thing or two about Copper-clad. He knows a thing or two about a lot of stuff, and a lot of people from all over the place. So thanks everybody for joining in. But really, what I wanted to ask you, Peter, is when these guys have questions, and I told them bring your questions because this is a great opportunity. Do you want me to interject while you're going, or do you want to save questions to the end or anything? How do you want to handle that?
How do you usually do it?
I like to just take them as they go, personally.
Okay.
But that's up to you.
I think that would be fine, and quite honestly, I will answer what I can. I might have to plead the fifth on some, but
Perfect. Sounds good.
All right. So, are you giving me control of the screen?
You got it, man. It's all yours.
Okay. And so you can see this introductory page.
Yep.
The beautiful copper-clad aluminum that's there.
We can see it.
Okay. Good. So, first off, we're going to talk a little bit about the history of copper-clad aluminum, and as you can see from these conductors here, these are 600 volt type conductors. That's where the majority of the work has been done with copper-clad aluminum up to this point, and you can see there's quite a variety of products that can be made from it. It's I guess from the left, you've got some THHN, different sizes, up to say 500 MCM. You've got some NMB type cables, and we do also. I mean, CCA is also a product that can be used in MC cable, and that's one of the primary uses for it. So it's got a wide variety of uses, and it was, like I said, Copper Weld was founded in 1915, and in Rankin, Pennsylvania, and moved to Glassport shortly thereafter, and was basically one of the, I feel, I'm biased of course, but I think it's a national treasure. It's endured the test of time, and it's a testament to the endurance of bimetals. Copper weld, at least the bimetallic division, which was the principal part of the business for most of its existence, made nothing but bimetals, and it's a testament to the product. So today we're in Fayetteville, Tennessee, and we have a facility there, and we've been making copper-clad aluminum there since 1973, 1974. That is debatable about which year we actually started making CCA, but the plant has definitely been there since 1973. And you know, we didn't start out making CCA. We created CCA because of the need. There was a copper shortage. The Asian wars created this shortage of copper due to the need for brass in the country. And you know, Korea first, followed by Vietnam. And it created an environment where, you know, we needed to stretch the supply of copper. Copper is a very valuable resource. Take nothing away from it. It is one of the most important industrial metals to our future, and it must be conserved. So part of the history of CCA is its entrance into code, right? In '71, it made code after a very extensive fact-finding study by UL. UL was instrumental in seeing this product come to life, come into the market. There has been there were studies began in '69 and '70, and over that period, it was found to be an effective and reliable material for conductors. So it's something that, you know, industry needed. There was a scarcity of one resource, and there was a need for, you know, conductors, and CCA basically filled that gap. So
brass.
Go ahead.
Brass is an alloy of tin and copper. Is that right? If I'm not mistaken.
Brass is an alloy of copper, zinc, and/or aluminum.
Oh, is that what it is? Okay. But when we need brass, we need copper, and
right.
You know, it's a sad fact, but during a war, you need brass, and that means you need copper, and it's a finite resource.
That's exactly right. Brass is an alloy, right? We'll get into this a little bit later, but, you know, copper-clad aluminum is like an alloy in that it's one metal, right? It's one metal, but it has two distinct metallurgical zones. It has copper at the periphery and surface, and an aluminum core, right?
Yeah, I'm gonna hold up a piece of the rod so the people at home can see it. So I mean, it's aluminum, and it's clad in copper, as the name would imply. So I just wanted to quickly, in case somebody had never seen it before, you know, so they at least can visualize what we're talking about.
Yeah. So what you have in your hand is a piece of rod. No, it's not like a straight rod like you'd think of a ground rod. I want to make that distinction. We're dealing with the electrical folks, so I'm sure you're envisioning a straight rod, right? But copper-clad aluminum rod is in a coil, And let me jump down to a picture of the coil. This is our starting rod. So it's probably not what you visualized being a rod. This is a rod coil. And so after our cladding process, this is what the rod looks like. And you've got copper on the outside, on the periphery and the surface, with a bond. I don't want to get too far ahead of myself, but that's sort of what you're looking at. So when you visualize, when you see this definition in chapter 1, and it reads conductors drawn from a copper-clad aluminum rod, that's what it is, right? It's not a ground rod or a rod that you might be thinking about. So, and the copper is metallurgically bonded. That's a key word right there. A metallurgical bond is essential to creating one metal. When one metal exists, there can be no galvanic corrosion between two dissimilar metals. And that's a pretty heady concept and hard to believe, but it's the absolute truth. So when you bond those two metals together, the interface of the metals actually unite and create basically an alloy layer, a brass layer. That's what a metal, in the case of this type of bimetal, CCA, you have a brass layer that's actually stronger than the two metals that it's connecting. But we'll get into that when we start talking about the process. But these are some cool photos. These photos here on the bottom, I actually took them walking through various CCA installations from the 70s. Copper-clad aluminum was installed after MADE code in 71. There was a time where the product safety standards had to be created. There was no CCA in any of the product safety standards, so that they have to be written in. So once they were written in, then you could list the product, right? So once you got the listing, then in 72, it started hitting the market. So from 72 to 1980, 79, 80, that was the first era of copper-clad aluminum. Why is 1980 important? Why couldn't it have just gone on? The Vietnam War ended in 79. There was no need for so much brass. The law of supply and demand, did its thing. The invisible hand of Adam Smith, worked its magic, and copper prices fell. And when we're talking about big commodity markets where 2 or 3 points makes a big difference in if a product lives or dies, right?
Sure.
So because you have to upsize copper-clad aluminum and code for your installation, when you have that much more material, and copper is inexpensive, then that simply can't compete.
Sure.
in the economy. So it basically took a dormancy period for 3.5 decades, basically. Went to sleep, went off the market, and that was the end of that era.
So what brought it back then? I mean, if we fast forward to the last 5-7 years or so, I mean, is it simply that you guys can manufacture it more cost effectively and therefore it's worth doing, or what do you think has happened?
Well, there was an inner period, from 1980 to around 2004, 2005, where copper-clad aluminum, if it wasn't for data cable and the fact that CCA used in data cable at high frequencies, the current travels on the skin, right? For 600 or 60 volt or 60 hertz, excuse me. It's late in the day. 60 hertz. 60 hertz conductors, like electrical conductors, it's primarily the current travels to the core. So it's important to have a bigger core, when carrying electrical current, to have the same resistance as, say, a copper conductor would. So, but in coaxial cable, for example, data cables, it's all skin. So the skin is more important for the data conduction.
Right.
And copper-clad aluminum survived all those years in the data business alone, making data cable.
Okay.
Very quietly going along its way. Copper Weld was able to carry on with its business, modest growth year over year, and until copper prices started rising. And I'm not an economist, so I can't speculate on why they're going, why they're rising in price, but they just are, and they have been since 2005. There's been some bumps in the road where they get a little bit less expensive, or lower, if you will. But generally speaking, they're at a point where copper-clad aluminum is cost effective, is economically viable, and that's why it's back.
Okay.
Mm-hmm. So that is just another thing about the history part. So this, of course, is probably the most referenced table in all of code. It's 310.16, table 310.16, and a lot of people didn't realize until we started making folks aware that aluminum and copper-clad aluminum share a table or share columns in this table, and even though they're different metals from a code point of view, for ampacity, they're the same. And it's important to make that distinction in ampacity, because from a termination point of view, their copper-clad aluminum is more similar to copper than to aluminum. In fact, it's a similar metal to copper. Probably the better term to use, it's more alike to copper.
I've got some of your NMB cable here, and it threw me for a minute, because I kind of got spoiled as an ex-inspector with yellow jacketed cables and white jacketed cables. I remember back when it was all white, but having yellow and white kind of makes it nice. And when I first got this, I was kind of thrown, because this is a white jacket and it's 12.2. Mm-hmm. But that's because it's a 15 amp cable. It's not a 20 amp cable, it's a 15 amp cable. So it's kind of nice that it's white, because in ampacity it's comparable to 14 gauge copper, right? You're not going to be putting this 12.2 for your bathroom and your kitchen and everything else, because it's not a 20 amp wire, it's a 15 amp wire. So it's the same current carrying capacity as aluminum, because it mostly is aluminum.
That's exactly right, Ryan. The color, that's not an industry standard, but it's a, let's just say, an industry tradition.
Yeah.
That's probably the best word, that your 15 amp conductors in that class, that product class, NMB, are white, right? Your 20 amp conductors are yellow. Your 30 or orange. And so that's sort of how we went about it. Now, hats off to the world of the inspectors. I went to a lot of inspectors meetings early on, even before we made the first investment in bringing this back. I'd show up with my little prototypes and say, "Hey, what do you think about copper-clad aluminum?" And they gave me a lot of direction on how to color code the jacket, right? And so there was a lot of study, a lot of research that went into that. And so far it's been great, because we know that the product is being installed correctly. and just by virtue of the fact that the color is the same as say a 14 gauge copper,
Right.
14-2, you know. So yeah, that was big. I mean, back in the day, back in the first era, that wasn't always the case. See this one right here? That's a black 12-2. This cable right here is a company called AIW, American Insulated Wire. They were a very strong manufacturer back in the day, and I'm not sure what this one is, but General Cable used to make. They had a brand. In fact, let me see if I can't jump over to show you something really quick. This might be kind of interesting. Can you see that?
Yeah.
These are just a small number of manufacturers of copper-clad back in that era. You could see this is General Cable. That was the one of the largest manufacturers of wire and cable in the U.S. at that time. Here is the black cable, AIW. That was actually owned by Leviton.
Oh, no kidding.
Yep. Collier. All of these companies are different companies now. Here's one Triangle. So a lot of change, but you know, one of the reasons, you know, that it got into code so easily back then was the fact that, you know, these companies needed material, right? They had customers that needed service and needed material, and you know, copper was there was a scarcity of it, and so they actually got behind the effort to bring copper-clad aluminum into reality and into code. The actual inventor of the equipment was a company called Texas Instruments. I'm sure you've heard of those guys. So a gentleman named John Fan, he was the inventor, and he worked for Texas Instruments, and he was actually the guy that went to UL, knocked on their door, and this was after, you know, all the issues with single metal aluminum NM cable, and said, "Hey, I've got this great product, and I'd like to do some testing on it because I want to get it into code, and I want to eventually list it." And you know, it's kind of funny. Imagine yourself sitting at UL behind a desk, and this guy walks in the door, and you just went through, you know, and this guy saying
what they went through with aluminum. Well, you know, and that's one of the funny things. I mean, you mentioned how it's metallurgically bonded copper-clad aluminum is, and we're going to talk about how it's built and everything. But I think so many times, and you've heard this 10 times more than I have, people just they ignore the first two words in copper-clad, and they just focus on the aluminum, and they say, "Oh, it's aluminum. If it even has the word aluminum in it, I'm not going to have it." And I mean, I kind of liken it to water. Well, you know, I mean, water is what? Hydrogen and oxygen. Well, but don't think of it as hydrogen and oxygen. Think of it as water, because that's what it is. You know, this is not really copper and aluminum. It's one thing. It's copper-clad aluminum. That whole thing is a noun. It's not.
Yeah.
Aluminum is not the noun, and copper-clad is the adjective. It's
I
one
mean,
thing, right? It's copper-clad
Ryan,
aluminum.
I mean, one of the things that, I mean, I say this in jest, but I'm also half serious. I'm thinking about making a public input, you know, next cycle, to change the name to aluminum cord copper. See if that'll make a difference.
Right, it would. It would too. Yeah, people would hear that and they'd say, "Oh, it's copper. We're good." Well, you know, they did that. They did that with manufactured homes and mobile homes, right? They're the same thing.
Yeah.
There is
Yeah.
no difference. They just changed the name mobile home to manufactured home because people would say, "Oh, he lives in a mobile home. Look at him." And this guy lives in a manufactured home, and it's like, well, they're the same thing, dude. You know? But yeah, it's the perception, you know.
It is, and that. But in all seriousness, we're going to try to re- change the perception, right?
Yep.
Follow the data, because imagine that. I brought up the point about the fella at UL back when copper-clad aluminum walked in the door. I mean, that person had to make a choice. Do I just say, talk to the hand? There's no way I'm going to mess with anything, or should I do this? Should I follow the data,
Yeah.
as this gentleman is asking me to do? And UL followed the data. UL set up the testing. They learned an incredible amount the decade before about conductors and how to test them. And they rolled up their sleeves and made it happen. Because, look, we all know this, necessity is the mother of invention, and there was a copper shortage, and solutions needed to be made, for God's sake.
Yeah.
So that's what happened, and that's why we see it today.
No,
The hard work of those folks.
there was a question from one of the people, and he said it sounds like the answer is no. But was there ever any sort of a problem with CCA in the past? I'm not aware of any.
Not that I'm aware of.
Yeah.
I mean, there's always going to be issues with poor workmanship,
Sure.
misuse, abuse. You can't get away from that. I mean, today, I don't know how many residential house fires there are. I'm sure that data exists, but there's more than a few, and many are electrical fires, right? There's been no documented case that I'm aware of.
Okay.
And but again, electrical conductors are, they're in a difficult spot. They play in a rough neighborhood,
Yeah.
So anyway, how is CCA rod made? I'm sure everybody's on the edge of their seats. So this is our starting point. This, as you might devise, is aluminum rod. This is how we receive our aluminum rod, and we have some very good suppliers, very respectable suppliers of this material that we've had long-standing relationships with. That dare I say, we love them, and we appreciate their service to us. And but this is how we start. It's we start with an 8000 series aluminum core. And Ryan, do you know what 8000 series aluminum is?
Well, I know that
Are you familiar with that?
it's the bigger and better alloy, right? Because I mean, pretty much everything is an alloy. I mean, to get pure aluminum is probably not possible, so they create an alloy, probably improving it, and from my understanding, it's basically the newest and best alloy that we have for aluminum conductors. I think they started requiring that in the early 80s, if I'm not mistaken.
Mm-hmm. Yeah, that's basically right. I mean, you can have alloys of non-ferrous metals. You can have alloys of ferrous metals, ferrous being steel. Stainless steel is essentially an alloy of basic carbon steel. 8000 series aluminum is an alloy of 1350, which is 1350 is the purest aluminum you can get. It's not 100% pure, but it's pretty close, and it's electrical grade, right? 1350 by far is the most widely used grade of aluminum for long haul conduction,
Mm.
utility grades, type applications. But for building wire, we use 8,000 because of its mechanical characteristics. It was designed to have similar thermal expansion characteristics to copper at the temperatures that are typical of circuits. And it's actually what this is a good question for you, Ryan. What metals are inside of 8,000 series aluminum? Do you have any idea?
I do not. I don't have a clue.
I'll get to the chase. But copper is in one of the alloying elements.
Oh, no kidding. Okay.
Aluminum, as is Fe, iron. The iron is used in the grade to give it mechanical properties, right? To make it more malleable, more forgiving, right? When you're making your terminations. And the copper is there to offer thermal stability. There are certain grades that use silicon and other alloying agents to give it thermal stability, but copper is used to offer, thermal stability to the characteristics.
Okay.
So that's, in fact, most of our scrap goes into 8,000 series aluminum for use for electrical purposes.
Okay.
As you might imagine, over almost a half a century of production of CCA, you generate a lot of scrap.
Yeah.
And it doesn't all go into the landfill.
Yeah, I can imagine not.
It's melted. No, it's melted down and turned into 8,000 series aluminum, turned into brass. Certain duplex stainless steels use CCA to achieve the goals that those materials shoot for. And so it's a sustainable product. And anyway, so we use this core, right? There's our aluminum. We buy it, bring it in, then we take copper strip, and we mechanically put those two together in our cladding mill. I've got a little diagram down here, very basic. This is the copper weld cladding process. We use oxygen-free copper, and this stuff is the cleanest, most thermally stable, and the most corrosive resistant copper that you can buy. And we use it because it basically clads so well. Our scrap production goes down big time when we use this grade of copper. And so it's a benefit not only for our production process, but for the consumer, because at the surface you've got very, very pure copper for connection purposes. So this is the magic, right? So and this is all done in line. We take this coil right here, or take this coil, these coils, and we start here. The strip comes in. This is all in line. We take an initial draw to size it, to make it completely round. Aluminum rod might come in the shape of an egg sometimes. It's not completely round, so you need to draw it to size it. But then it enters an oxygen-free chamber, right? And why do you think that's important?
Well, I mean, the thing about oxygen, and somebody the other day on Facebook I saw, they said, well, I'm still going to put grease on my copper-clad aluminum. Well, the antioxidant compound, when you install it correctly, when you actually follow the instructions, the first thing it says that you have to do is you abrade the aluminum wire. You have to scratch the aluminum wire to knock off the layer of aluminum oxide that's on there, because that's the problem. is the oxide on the surface of the aluminum. So once we get that off, then they can apply antioxidant compound and what have you. But what you're saying, if I'm understanding what you're saying, is you've got aluminum in an oxygen-free environment. It couldn't possibly create aluminum oxide because it requires oxygen and there is no oxygen. So there's no possible
That
way for it to happen.
that is exactly right, and that's why that chamber exists. Essentially, and this picture is pretty telling. This is the oxide layer. This is the aluminum. We're taking a shot with our scanning electron microscope. This here is just medium. It's like just the medium that we use to take the picture. It's not copper or anything. This is so you can actually see
Oh, okay.
the oxide layer.
Yeah.
And these are microns, so you could think that it's probably what 2 microns in width.
Okay.
Now you're not going to be able to see that with the naked eye,
Right.
right? It amounts to, gosh, 15 to 30 angstroms if you're into
Oh
those
yes.
types of measures.
Peter, listen,
You
you're in
know about
America.
angstroms.
You're in America. The only people that understand the metric system are scientists and drug dealers. All right, I'm not either of them. Never have been either of them. So I kind of think I know what a micron is. I don't have any clue what the other thing you just said is. An angstrom or.
I mean, that's one of my Achilles heels. I've been in the metals industry since I was 12.
Okay.
So, no, actually since 91. So, making wire and making metals, steel, then I moved into non-ferrous metals, then into bimetals. So it's, been a 30 some odd year career of talking angstroms. So sometimes I forget that people don't understand those terms.
Right.
But anyway, grades and angstroms and alloys, that's my world. But to make a long story short, this layer here is the issue, right? This is a layer of aluminum oxide, and aluminum oxide is an insulator, meaning that current has a very difficult time passing through it, be it data current or electrical current. And so if that is there and you make a termination over it, and you don't crack it sufficiently to allow the current to flow through, you're going to have a restriction of that current. The current density becomes an issue because you're trying to push that current through smaller and smaller spaces, and that tends to generate heat, right? So what you're saying is, correct. You try to get off that oxide by scraping it and scrubbing it and trying to get that layer off, but the dirty little secret is that it reforms in a split second. You can't. So you got to put the oxide on it, oxide inhibitor on it first, and then when you're scraping, hope to God that you don't rub off that oxide inhibitor and just allow it to reform.
Yeah.
But aluminum is an excellent conductor, by the way. I mean, for an industrial metal, it is phenomenal. I mean, where would we be without aluminum? So, but you got to deal with this when you're making terminations. You have to deal with this layer, and so that's what we do. We try to eliminate that anxiety, for the marketplace.
So you have that aluminum rod sitting out in the warehouse or the manufacturing facility. So you put it into the chamber, and you mentioned you have to draw it, you have to get it the right size and shape and everything. And then I imagine that the scraping of the oxide layer happens while you're applying the copper layer? Is that and that process is a one
Right.
step thing?
It's a different plot. It's a process that happens inside of this oxygen-free chamber. This is the special sauce. I can't show you this. I
Sure.
can just demonstrate it to you in a box.
Yep. Yep. Understand.
But the concept is you got to scalp off, you got to remove 100% that aluminum oxide.
Yeah.
And imagine this rod is moving at a constant speed, right? It's moving. So, this is all a dynamic inline process. All these things are happening at once. So the rod enters the chamber, it's clean, and then it's basically, this is where the other magic happens. Through a series of welding and pressure, we create that metallurgical bond. We create that alloy layer. Alloys are created when heat, melts them together, basically.
Yeah.
And so at the point of union, that pressure is so high that the heat from that bonding process creates that metallurgical brass layer. Now, once that happens, it ceases to become two metals, and it's a bimetal.
So you could give me the sharpest blade in the world and all day long, and I could not scrape the copper off and just get there's not like a point of transition where it's no longer it's melded together, right? I mean, is that
Right,
a fair way of
right.
saying it? I mean, if I wanted to strip this copper off, I would have to get chunks of aluminum coming off with it, because it's not like it's
Yeah,
you know
exactly. I
yeah,
mean, you can certainly try,
right.
and many people have. You can dig down into the aluminum, but yeah, I mean, more than likely you're gonna take off a chunk of aluminum along with the copper that you
Right.
just removed, because it's bonded. I mean, think of it this way. I'm pretty sure not a lot of our viewers tonight have seen a wire mill,
Right.
but what a wire mill does is take that rod that's in your hand and it draws it, meaning stretches it like a rubber band. And that's the type of physical force that's applied to that metal. And guess what? It's done cold. So, our wire drawing machines pull that diameter down from, nearly an inch across in diameter down to a 12 gauge wire. And in certain cases in the coaxial business, down to 24 gauge wire.
Right. So one of the comments, and this struck me too, is one of the guys said, "Wait, so there actually is such a thing as a wire stretcher?" Yeah, you can't get it out of the truck, And one of the other questions was just point blank. Where did it go? What's the biggest pro and the biggest con of copper-clad aluminum?
I don't know if I'm qualified to answer that. I mean, because there's so many points of view, right?
Sure.
So I would suggest that you try it out. Quite honestly,
Sure.
For a product to be safety listed, to carry a listing, it's got to be, or it's got to meet a certain minimum requirement, right?
Yeah.
And all conductors that are in the market meet or are referenced by code, and all products, all conductors have a listing, carry a listing per code. So as far as pros and cons, I mean, you've got advantages and disadvantages to everything.
Okay, fair enough.
But one of the, if I can offer anything, it's probably, the weight is different from copper.
Okay.
Right, especially in small circuits.
Theft resistant, right?
And it is a theft deterrent.
The theft
I wouldn't
deterrent.
say
Yeah. I guess it
resistant
can't be
because-
resistant, but yeah.
Yeah, I mean, it has about 1/10 of the scrap value of single metal copper scrap.
Yeah.
So, some people don't think it's worth their time, right?
Right.
So, yeah.
There was another question, and I'm gonna see if I can take a stab at this. He's saying, okay, well, look, I understand that the aluminum inside the wire won't have any oxidation, and the copper won't have any, oxidation. But what about the very end of it where you cut it? And my thoughts are, and tell me if I'm wrong here, I, I guess it could oxidize, but the next question is, so what? Right? Because when you terminate it, you're using a set screw lug that goes into the copper, or you're using twist-on connectors that go onto the copper. I'm trying to think of the importance of the very exposed end of the wire, whether that oxidizes or not. And I can't think that it would matter. But I don't know. Am I wrong on that?
No, I don't think you're wrong. I think you're dead on. And it goes back to what is the philosophy in terminating wire, right? Ryan, I'll ask you this question. What happens if moisture gets into the interface between current and material?
Bad stuff.
Bad stuff.
Bad stuff.
Bad stuff. And what's interesting about the engineering and design of connectors is that connectors are designed to keep moisture from entering that material current interface, right?
Yeah, right.
If when that happens, you're going to get a short circuit of some kind, right? That's
sure
more than likely what's going to happen. So connectors are designed to keep moisture out of there. It's anything that's conductive. Connectors are designed to keep that dry.
Sure.
Even connectors that go underground or outside wet environments, those connectors are designed to keep that interface dry.
Yeah.
And one of the first things that I learned when I entered the metals industry is that galvanic corrosion cannot happen unless there's a median or a medium that allows for the conduction of the current between two dissimilar metals. And if that medium doesn't exist, meaning moisture,
right, electrolyte,
an electrolyte,
yep,
right? You sound like a metals guy.
I'm a metalhead. My favorite band is Slayer, and I like Megadeth a lot. So yeah, that's me. You got me pegged.
So in the absence of an electrolyte, moisture, you're not going to have galvanic corrosion. So one of the things that we first talked about, when you cut aluminum, or you say brush off the surface of aluminum, there's an oxide layer that forms instantaneously. So all of the aluminum that you see exposed has a oxide layer on it, which means it's not going to oxidize anymore. That's aluminum's mechanism for protecting itself. That keeps it from oxidizing.
That's the scab over the wound, if you will.
These products, guess what? These products can't be used in wet environments, these NM products, right?
Sure. So
there's never going to be exposure unless there's some kind of misuse or, negligence, something that, us as a manufacturer of cable, we can't control that, So that's why, and I'll show you something interesting since we're on this. I'm sorry for jumping around, but it is apropos.
Yeah.
I pulled this out of a house in Tennessee with my very good friend, Steve Mallory, who works with us. Steve is a certified electrical inspector, and he very graciously joined our staff as our inspector on staff. And he and I, back in the day, this is way before he came to work with us. This is when he worked as an inspector in Tennessee. He showed me some of Uncle Joe's work, and And I always carried this around, not to praise the workmanship, but to show folks that, even in the worst conditions, copper-clad aluminum is pretty forgiving. And this came out of a kitchen remodel, and it's the original wire from the 70s, but this remodel was done probably, oh gosh, early 80s maybe. And I don't see any galvanic corrosion there.
No.
And the reason is because NM is used for dry environments. This came out of a kitchen. This is a number 10 wire. And, even he nicked it up here and still no galvanic corrosion. One thing's for sure, if there are, we estimate that there are some 150,000, residential installations made with NM cable in the era of 72 to 80. And one thing that I do know for certain is that all the electrical connections in those, and there are millions of them, they all have cut ends.
Sure.
All right. So so we talked about the manufacturing process, and we talked about a little bit about this, but maybe we'll underscore this. So Ryan, pop quiz. How is CCA different from aluminum?
How is copper-clad aluminum different than aluminum?
Yep.
All right. Well, I'm gonna go ahead and say that one has copper cladding and the other doesn't. So I'm not sure. I'm not quite sure where you're.
So far.
Okay. Yeah.
You gotta...
I'm not quite sure what you're fishing for, but if you're trying to catch a sucker, you probably just did.
Well,
yeah,
number one, copper-clad aluminum doesn't have this rascal.
Sure. No aluminum oxide.
That has been evacuated. That is no longer part of the equation. So what has happened is that we replace this material here, the aluminum oxide, which is an insulator, and we replace it with oxygen-free copper.
Yeah.
And we metallurgically bond the two. And so when we do that, it becomes a different metal, right? And I've got a little thing here. This is a transversal, shot of what it looks like if you take a slice, like, with a cheese slicer, and
Okay.
you look at it crossway. It's not a small amount of copper, right?
No, it's not. It's a surprisingly big amount, to be honest with you. It's a deceptively big amount, I should say.
Yeah. And it's 12 gauge, and I guarantee, Scout's honor, this is not a doctored photo.
Yeah.
This is comes right out of the micrograph.
Huh.
But you would, looking at it this way, it probably makes more sense. But copper-clad aluminum to the ASTM spec must be 10% cross-sectional area, right?
Mm-hmm.
And 27% copper by mass.
Mm.
So you're looking at a chunk of copper on there over your aluminum, right?
Yeah.
So one of the jokes I make to anybody that'll listen, to my wife on occasion, I'll say, "Honey, what's the best oxide inhibitor you could have for an aluminum wire?" And she shakes her head. And I've heard this a billion times. 27% oxygen-free copper.
Wow.
And she doesn't laugh.
She doesn't laugh, and she doesn't know how lucky she is. I mean, to be able to come home to that every day. I mean, man.
I tell you. So, we wanted to demonstrate, okay, how is CCA different from aluminum scientifically? Let's get some data points. We know the physical characteristics are different. The weight is different. But what about if we run some current through it and compare
Yeah.
size for size? Because remember, they share the same column in this chart here. You know, the electrical world treats them the same way, right?
As far as
But are they
ampacity
really
goes.
the same thing? So we did a little study here. This orange line is 12 gauge copper-clad aluminum. I guess the off orange line is 12 gauge aluminum, and we ran 25 amps through them both, and we measured the heat, and come to find out that the copper-clad aluminum 12 gauge ran considerably cooler than the aluminum 12 gauge.
Okay.
So how do you explain that? The only thing, only reasonable explanation, the one that we sort of, adopt, is that 27% copper cladding really helps.
Absolutely.
As far as giving off the heat, right? So this is and at 35 amps, it's even more pronounced. This is 100 C, right?
Mm-hmm.
So 90 C is kind of the Maginot line, right? That's when insulation starts to melt.
Right.
And really, we don't ever want to go over 90 C. But even at 35 amps, this 12 gauge CCA, and by the way, tell me, Ryan, again, remind me, what's the standard ampacity for 12 gauge CCA?
For 12 gauge, it's 15 amps, right?
That's
On a
right.
60-degree column.
So yeah, and that's the way most of it's employed, right?
Sure, yeah, it's in
Installed.
NM cable, so it's going to be 60 degrees.
For small circuit conductors, because of the 240 rules. But here you're more than double the legal ampacity, and it's still under 90.
Right.
So this kind of data is telling, and but anyway, that's how it's different from aluminum. It's interesting that, and I don't have a graph on this, so I don't have anything that really shows how copper and aluminum compare, or copper-clad aluminum compare from a heat rise point of view, but or straight conductor resistance. But generally speaking, copper-clad aluminum is slightly, when you upsize it, right? When you upsize it per 31016, is slightly more conductive. There's less resistance in the CCA when upsized, right? Than your equivalently rated copper conductor. So it is, we're not pitting one material against the other,
Right.
but this is what the data is told us, and we've assembled quite a library of data.
Well, I mean,
over the last 6 years.
The fact is, in the NEC, when it comes to ampacity, we have two basic things. We have copper and we have aluminum. CCA is not pure copper. It's not going to have the same ampacity of copper. Therefore,
No,
it's going in the other column. Because there's only two.
that's right.
And that's that. I mean, could we develop a third table that just does CCA? Probably, and it would probably end up between copper and aluminum, and you might gain an amp or 2 amps or something.
Mhm.
So A, is it worth it? I don't know, but B, it's not there now. So when it comes to sizing the stuff, it ain't copper. It's everything else.
That's
It's-
right.
It's sized like aluminum.
And that's the safe place to be, and code is built all around safety. That's what it's all about. And quite honestly, it's not a bad place to be in this column,
Yeah,
simply because we know we're safe, right?
absolutely. Yep.
One of the things that I tell people is that the Copperweld is a 107-year-old company. We have a very proud tradition and a brand to protect. We're the most conservative company on the planet, and in my opinion.
Yeah.
But quite honestly, we're not in the business of putting the public in danger or putting a product where our brand would be tarnished, right?
Yeah.
Putting a product out there. So we believe in research. We believe in performance testing. We believe in NRTLs and third-party testing. We believe in the NFPA
Yeah.
and the good work that they do. But we're all about testing and data,
So
and that drives our decisions.
on the testing and data part, there's a question that came up on the chat board on YouTube, and it comes up all the time. I hear it is about expansion and contraction.
Mhm.
What can you tell us about that? Because I'm well. I'll put the ball back in your court. I am a metalhead, but you're the metals guy. So your turn.
Well, it's probably a good time to talk about what makes a good termination, because I'm sure the expansion question is all about terminations.
I think so. Yeah, and I think that the terminations are what people really need to know about, in my opinion.
One of my I guess mentors in the non-ferrous installation world told me one time that, and correct me if I'm out of line here, because I certainly don't have your extensive experience being a inspector or an ex-inspector. Once an inspector, always an inspector, right?
Right.
Ryan?
Absolutely.
But terminations are an issue, right? That's a lot of problems. Dare I say 80% of the problems that happen, in electrical installations happen due to, poor connections. Am I off base there saying
No,
80%?
if anything, you're low. I think it would be probably even higher than that.
Okay. Well, I mean, this is the reason that I want to talk about this, because after long consideration, I mean, we did a lot of soul searching and thinking about this before we decided to bring back copper-clad aluminum, into the market. What makes a good termination? And we, after thinking about it and sweating over it, and many months of toil and going back and forth with contractors and electrical inspectors and people that understand these things, it comes down to thermal stability, long-term, conductive surfaces, long-term, and galvanic stability, long-term, right?
Okay.
Obviously there was an issue with aluminum early, like in the 60s and the 70s, before the remediation of it through the ad hoc committee. There was an ad hoc committee that was assembled in the early 70s whose job was to remediate the small circuit aluminum conductors that had been installed in throughout that decade. And it resulted in the material being delisted and exiting the market, so to speak. But to make a long story short, most folks think that it was because 1350 aluminum was being used, which is perceived to be thermally unstable, or not stable enough. When it gets hot, it tends to move, right? So thermal stability is important in terminations, because if you get any distance between your contact and the wire, you can have arc faulting. and arc faulting is not good. I mean, it's um, you're talking about temperatures upwards of 3,000 C. So that steel, plastic, wood, nothing's going to stand up to that, right?
Right.
So thermal stability is important for arc faulting. But you also have to have conductive surfaces, right? So aluminum is an excellent conductor. It's an excellent conductor when it's sized appropriately. And at 60 hertz, that current's going through the core up until the point that it makes its termination or splice.
Okay.
And then it's got to pass from the core through what? Through the surface.
Mm-hmm.
It moves in the direction of that load pull. I don't know if those are the correct words, but those are the words I like to use because
fair enough.
So that surface has to be very conductive for the current to get through the splice or the termination to do its job. And then thirdly, there can't be any galvanic corrosion going on, right? Similar metals have to terminate. And as I alluded to earlier, in the absence of an electrolyte, you're not going to get, too much galvanic corrosion, even if, and this is controversial, but I'm here to say it right now. In a dry environment, galvanic corrosion is not a big deal. And because there's no electrolyte there to create galvanic corrosion. I'm not saying that
you're not recommending people splice copper to aluminum, but in a dry environment, and done perfectly, that's a different story than if it was done outdoors. Yeah, I think.
And there are other issues with aluminum that are really the root of the failure mechanism.
The conductive surfaces part, right?
Mm-hmm. And so, I'll leave it on this image, just to give the viewers the idea of where I'm going with this. So 1350 aluminum, if it's in a small circuit, say, a 15 amp circuit or a 20 amp circuit, and you splice that thing, and there's no oxide inhibitor on it, right? How are you going to put oxide inhibitor on a small circuit like that,
right?
Unless you use some kind of a twist on splice connector or some kind of splice connector that has it in there, or that breaks this layer. But if current can't pass through there or is restricted, the current density is massive, trying to force its way through cracks, you're going to get heat. You're going to get more heat than normal, right? I'm not saying every time, because there's a lot of aluminum to connections out there that have lasted. So that's the peculiar thing. It's not an every time thing where aluminum will overheat, but where you've got restriction of the current, that's where it happens. And 1350 having thermal characteristics lower than that of 8000 series, it's affected more when this heats up. So this is a controversial subject. Obviously there's some failure mechanisms that that are general knowledge, but we have to remember that aluminum is an excellent conductor. It's just that it has to be treated correctly and terminated correctly. Right. So
how do we terminate copper-clad aluminum? I've got, this is copper-clad aluminum that I have in my hands, some NM cable, and when I put it under a twist-on wire connector, it's copper touching copper. And that's that. It doesn't seem to me that I should need to do anything too out of the ordinary to copper-clad aluminum, because it's copper touching copper. It's not the copper touching the aluminum part. You guys already addressed that, right?
Mhm.
In the field, I can't even touch the aluminum part if I wanted to. So it's copper to copper. So can I just put a regular, twist on wire connector over it? Or can I land it on switches and receptacles? Because these are and you know this, these are the questions the guys in the field are just hitting me over the head with.
Right, right. So, as you know, it's a mixed bag, right? And obviously, in code, in 110.14, CCA and copper are seen as similar metals.
Yep.
Meaning, for this application, electrical connections, copper-clad aluminum and copper are similar, right?
Yeah.
So this is from the 2020 cycle. This is the second revision committee statement from Code Making Panel 1. And it reads, copper and copper-clad aluminum have been deleted from the dissimilar metal list for the application of this requirement, right? So, and then in this cycle, in the 2023 cycle, Code Making Panel 1 reconfirmed that.
Yeah.
Nobody argues that CCA and copper are similar metals.
Yep.
A growing number of people understand the science behind it and why that's so. It's certainly not everyday common knowledge. It's not like Wheaties. Everybody knows what that is. But the plain fact of the matter is it's from a termination point of view, it's
copper.
more like copper,
yeah,
than aluminum. And from a metallurgical point of view, it's a similar metal
sure.
to copper.
Sure.
So if you look at some UL guidance, are copper-only residential light switches, and this is the same one, are copper-only residential receptacles acceptable for use with CU-clad conductors? Yes. And this says, this comes from the guide information, the white book, the old white book,
Yep.
You can get all this stuff online now. Terminals of 15 and 20 amp receptacles, not marked Colar, are for use with copper and copper-clad aluminum conductors only. So here, UL is making the statement that in wiring devices, it's similar. So this is, even though this is not very good workmanship, this is how you terminate copper-clad aluminum. Of course, you not like that, but
right,
you can terminate with
I'm gonna screen grab that, and play it on a loop. This is how you terminate it. This is a
You're not.
but I mean, from a physics perspective, from an electrical perspective, we terminate it like it's copper, right? You size it like it's aluminum, you terminate it like it's copper, and I mean, really, that's it. Most of the discussion, I think we spent trying to clarify why we do that. Why does it carry current like it's aluminum? Well, because it mainly is. Why do you terminate it like it's copper? Well, because the surface is copper. It's really, it makes a lot of sense, quite frankly.
And the absence of that oxide layer, it's really, if that oxide layer existed, it wouldn't matter how much copper you put on there.
Sure.
Right. Or, that oxide, removing that oxide layer and replacing it with something that is conductive, that's really the science behind this. And the fact that we upsize it, derate it, if you will, makes it even more interesting, because of the fact that it's a very conductive material. And after I go through this, I want to move on to the some testing that we did through the bimetals task group.
Can I ask you
And
one more question as far as terminations
sure.
go before we move on though?
Mhm.
What about torque? When I have a torque value marked on a termination, how does that change whether I'm using copper or aluminum or copper clad aluminum?
Well, there's a lot of different equipment, circuit components that have torque requirements. We recommend that those be followed,
Mm-hmm.
but also we also identify certain torque requirements, and so there's direction from both sides. If you know if it comes down to it, the AHJ should contact us because we're you know this is a dynamic situation. This is a product that's being introduced or
Right.
reintroduced after a long dormancy period. So a lot of equipment manufacturers haven't caught up yet,
Right.
right? Their equipment is totally compatible with this product,
They just haven't
but
changed their instructions yet.
right.
Right. So
So we recommend that uh, that AHJs, the contractors, check with us first because we've done performance testing. We know what's going on with our terminations, and we give recommendations based on data.
well, and
So
I'm just thinking, yeah, I don't have a lug in front of me, but I'm just thinking when I look at a lug, it'll normally say something like AL9CU, so 90 degrees copper or aluminum or copper clad. Um, and then it'll give me a torque, but I'm just trying to remember, does it usually give two different values for copper and aluminum? I don't think it does. I think it normally just says 25 inch pounds, and there you go. So
I have to plead the fifth on that,
yeah,
but
and I do too.
I
I do
believe you.
too. Yeah, I could have just invented that whole thing to be perfectly honest with you, but I think it's the case. I don't think they really address one versus the other. Um, there was a
Yeah,
comment
especially
saying,
with CUAL. I obviously if it's aluminum has been around, for a long time, and is a well-known material. And
mm-hmm,
you know, if something is marked CUAL,
yeah,
you can bet that it's been tested with AL.
right,
So the terminating with CCA is just kind of an added benefit. You've got
yeah,
it's just like a copper wire, and you've got that extra diameter size to terminate nicely. I mean, good terminations, Ryan, and I think you'll agree with me here, are all about electrical contact and
sure,
surface area, good electrical contact. And when you upsize CCA, say you have a 14 copper here and a 12 copper clad aluminum here, and you terminate them around a screw or in a splice or whatever, just because you have more surface area with the CCA means that termination has more contact.
right.
The simple fact that the wire dimension is bigger, has more surface area, means that there's more surface contact at the termination point or splice.
Okay, so Chuck Mello chimed in and he said that I did not just make that up. So yeah, there's only going to be one torque value, and that's tested per the manufacturer's instructions and in accordance with the listing. So yeah, I don't see that it would I don't see that it would matter. It would be the same value whether it's copper or aluminum or copper clad aluminum.
Awesome. Well, thank you, Mr. Mello, for clarifying that. So, if I could advance to the bimetals task group,
Absolutely.
what happened in 2020? Does the NFPA encourage innovation? Yes. I think the NFPA is very progressive in how they allow for innovation and new products or re-emerging products to do their thing. And in the case of the Bimetals Task Group, after the 2020 cycle, the Standards Council of the NFPA gave an order to create, or a decision, I think decision is the correct word, to create a Bimetals Task Group. And they put it under the direction of the NEC Correlating Committee. And this task group was put together to essentially study copper-clad aluminum and, you know, the safety aspects, and in specific terms, 14 gauge copper-clad aluminum. So a group of 14 members came together, and it was of balanced interests. This is the decision, D19-2. It says the council directs the NFPA staff to establish a Bimetals task group of balanced interests to review the proposed changes to the 2020 edition of the NEC that relate to copper-clad aluminum conductors, and recommend changes through a tentative interim agreement at TIA, and or provide public inputs for the next revision cycle. So it was you know, there were competitors.
Yep.
on the panel. The American Bimetallics Association, the Aluminum Association, the Copper Development Association, the IEI was involved, Intertech, NRTLs, UL, of course, and branch circuit experts. You know, our Tom Dimitrovic was involved from Eaton. Chuck Mello was part of the task group, very important part. Mr. Brian Rock was part, and
devices.
You know,
yep.
Devices, and so the idea was to come together and try to figure this out. You know, and so what we did was devise a test plan, right? There was some direction given by Code Making Panel 6 that studies had to be done. So we put together an extensive test plan to test 14 gauge copper-clad aluminum at its proposed ampacities of 10 amps, 15, and 20. So what did we do? We came up with a test plan of advanced staging, you know, basically,
yep.
You know, based on 486C and 498 and 1567. So we basically assembled this test plan based on UL standards, you know, formal UL standards. And even though this was sort of a non-standard test, kind of compiled, you know, techniques from different standards. This is what we agreed to as a body, and we did the work in Menominee Falls, Wisconsin, at the Eaton Laboratories there, a very qualified lab, and the group decided that, you know, came to the agreement that it was third party enough, that the data coming out of there would be believable. It's not like there would be any home cooking or any, you know, fast shuffle and sharp dealing, you know, like they say in the South.
Right.
But what we found was exceptional, and you know, noteworthy. So we tested wiring devices, we tested circuit breakers, and we tested twist-on splice connectors. And other wiring devices, we had 4 different manufacturers. Of the circuit breakers, we had 3 different manufacturers, and of the twist-on splice connectors, we had 4 of the major U.S. manufacturers. And we measured heat rise, right? So the numbers that you're seeing on the screen are heat rise numbers over ambient. So
okay.
Say if you're working, working, with a 20-degree ambient or a 30-degree ambient, those numbers in bold are averages, over heat rise, or that were derived from the study. And the study was extensive. If anybody would like copies, I can certainly supply them. Also, they're massive. Be prepared to study a while.
Well, and if I can hop in, two things. Number one, you can get a ton of information on NFPA's website, because this was all transparent. So for the 2023 code cycle, if you look at the proposals in Article 310 especially, you can get the entire report, it looked like. And then the other thing is, so what you're saying on these numbers is the bold number is measured in degrees C. So I'm guessing you put it in like a what do you call it, a 35 degrees C ambient temperature or what have you, and then when you put the load on, then it increased by 6 degrees C. That's ultimately what you're saying?
Right.
Perfect.
Right. And so these numbers here, this is at 10 amps. Okay, this is at full 10 amps, and this is the copper-clad aluminum 14 gauge, and this is what we were studying. This is copper at 15 amps, full 15 amps, which, like I said, copper is a beautiful material. This is something that we need to preserve for our sustainable future. I mean, there's certain things that there are no alternatives for copper.
Right.
And, 15 amps, 14 gauge copper is like the Bible. Nobody questions that, right? That's the standard. And so, what this tells us is that, CCA at 10 amps, which was the proposal, generates less heat. That heat rise at points of termination. And these are like measuring here, like the thermocouples are measuring, how much heat is generated under this twist-on splice connector. How much heat is being generated here? How much heat is being generated at a circuit breaker terminal at these prescribed ampacities, or proposed.
Am I misunderstanding this, or is this just really surprising? I mean, you put it in a 20-degree ambient temperature, and for copper-clad aluminum, the temperature at the connection was 26.6 degrees. And you're saying that in the same room, the temperature at the copper connection was 31 degrees? Or am I misunderstanding that completely?
I think you're seeing it pretty clear. And don't blame me. This was Chuck Mello and Brian Rock's fault.
Oh, I'm absolutely blaming Chuck and Brian, no problem. But that's just so surprising. I mean,
and Tom
Mitrovich,
I want.
Yeah, and I can blame Tom too, no problem there. That just seems so counterintuitive, because, I mean, is that basically saying that the copper-clad outperformed the copper? That's sure what it seems like to me. I'm not a scientist, so I don't fully understand those numbers and the ramifications, but that's what it seems like.
I plead the fifth.
Okay, yeah, fair enough. Fair enough. Okay. Chuck is typing furiously, I'm sure.
All this information is public. This is just, a little summary sheet.
Yeah.
But the genius of this thing here is that, it's graduated, right? It's scaled not only to Ohm's law, but it's scaled to Fourier's law. And there's a connection between Ohm's and Fourier's. Fourier's law is the law of heat conduction, right? So when you come up with this guy, say at 60 C, 14 at 15 amps, it equates roughly to what aluminum would be at 12, right?
Sure.
I don't think, since copper-clad aluminum wasn't invented when this chart was, this is just kind of a glob on, right?
Yeah,
I mean, just
agreed.
Got to be better, worst case scenario. So
I see where you're going with this. So what I just said was not accurate at all. The copper outperformed the copper-clad. Is that right?
At size for size, yes, it
Yeah, that's
probably would.
at size per size. Yeah.
But
So.
when you derate it,
Mm-hmm.
it's a big difference, right?
Right. Right.
So all of these numbers are scaled to restrict heat or to limit heat.
Right.
Does that make sense?
Oh, absolutely. Those numbers are
Yeah.
there to limit the temperature on the insulation of the conductor, right? Because when those
So
wires fail, it's not the copper that melts, it's not the aluminum that melts, it's the insulation, right?
it's the
So
insulation.
so based on how much heat the insulation can withstand, we limit the amount of heat that the wire can produce, and we call that the ampacity.
That's right.
Yeah.
And it's, the Bimetals Task Group, which is an independent group, it was created by this NFPA Standards Council, but it's an independent group.
Mm-hmm.
And, what, and by the way, it created 19 public inputs
Mm-hmm.
based on that Menominee Falls testing. And what it tried to do is right here, add 14, and this 60-degree column, it would be 10, right?
Right.
And what it says is that when you run 14 CCA at 10 amps for, which would be used for like lighting circuits, LED lighting circuits, dedicated LED lighting.
Yep.
is one of the uses that could be employed. And you compared it directly with 14 copper running at full 15 amps, right?
Right.
This is what you'll get.
Oh, so that was compared to the different size. Okay, so we're looking at 14 gauge copper compared to 12 gauge copper-clad aluminum.
Right.
Okay.
Right.
Okay. Now that makes a lot more sense.
This is 14 copper.
Right.
This is 14 copper-clad aluminum compared to 14 copper.
Oh, it is size to size. Okay. Okay.
Yeah.
Interesting.
Yeah. Yeah. For equal ampacities is what this is. Yeah. And this is 14
Right.
CCA, and this is 14 copper, right?
Or is that a 15 amp CCA and a 15 amp copper?
No, this is a 10 amp.
Okay. It is size
10 amp
size to
CCA.
size, not capacity to capacity. Okay.
This is 10, and
Got it.
this is 15 copper. This is 10 CCA.
Okay.
So yeah, this chart could be a little clearer, but this is strictly relating 14 CCA
Yeah.
to 14 copper.
And it looks like a lot of comments from people that are interested in learning more about these and reading the studies. And yeah, go to NFPA's website and you can download them. Okay, so yeah, you can download them for free. Chuck just mentioned the sizes are the same. The 14 gauge CCA was tested on a 10 amp base, and the 14 gauge copper was tested on a 15 amp base. And we're kind of falling back on Chuck on this because he was the one that ultimately put the data together and presented it. And and I'm not going to speak for Chuck or for you, but Chuck comes from a product testing background, right? He was with UL and with Intertech. I mean, that's product testing is what Chuck does. So
Yep.
yeah, very, very well qualified to do the report.
Well, he had a lot of help.
Right.
There was very talented people in that task group, and let's face it, that was that task group was doing some pretty monumental work.
Yeah.
And I was honored and very happy to be part of it. It was a long slug, that's for sure. Nearly all of 2020, but
Yeah.
there was some good information, and like you mentioned, it's all public.
Mhm.
You can get those test reports from the NFPA website.
Yeah.
And if you want to contact me, I can certainly supply the test reports to you, and you can, you can crunch the numbers yourself, and make up your own mind.
Yeah.
I'm not here to, preach any one thing over another. I follow the data,
Yep.
and that's what Copper-Weld and yours truly are all about.
Yeah. So right now, we can, as far as the code is concerned, we can install copper-clad aluminum. We've been able to install it for the last 50 years. Some things may or may not happen in the 2023 code. That's not set in stone yet. But the things that are set in stone is you follow manufacturer's instructions. You size it like it's aluminum, and you pretty much terminate it like it's copper. Device terminals have no issue with it. Receptacles, switches, terminate it, not a problem. Wire connectors, some of the wire connectors might say for copper only, and if that's the case, what are you going to do? I mean, the fact of the matter is, did they ever even test their wire connectors with copper-clad? Probably not. It wasn't on their mind. Does that mean if they had tested them that they would have failed? Almost certainly not. I mean, again, when I use a twist-on wire connector, it's copper touching copper. It is. So I know I have a lot of people saying, well, the instructions for the twist-on wire connector says only copper. What am I supposed to tell an inspector? When they read that and they want to know, can you use it? I don't know. I mean, what do you tell them? I guess the appropriate thing is you have to follow the instructions.
The way that we interpret code, and is that, look, every circuit component has the right to identify its proper use, and that's what we do. But the key to identification is that it has to be backed up with performance testing. I mean, I can't go to a manufacturer of splice connectors and demand that they test my product.
Right.
But I have the right to test my product with a myriad of different components out there.
Sure.
I mean, a circuit is a circuit. Everything's interconnected.
Well, and
that's the beauty of the NFPA 70 is that it realizes that, and it leaves room for innovation.
So in 110.14, the rules for connections, the general rules, for connections and terminals, it says that the splicing devices have to be identified for the material. That's the code phrase. And the term identified is defined in Article 100 as being, quote, recognizable as suitable for a specific function, use, application, etc. So what you're saying is, look, we, Copper-Weld, we are identifying that product is suitable for copper-clad aluminum because we've tested it on copper-clad aluminum and we've used it on it, and it's not a problem. I mean, is that ultimately what you're saying?
Basically, I mean, we have 50 years of, or right at 50 years of historical substantiation. When these products started, back in the 70s to be installed, there were no, Colar or CUAL wire connectors.
Yeah.
We've pulled, many receptacle boxes and intact receptacles like these, and with splice connectors on them, and there's been no issues, right? So that's only part of the story, right? That's one data set that we have, but we also have performance testing like the Menominee Falls, that actually tested 4 different varieties of wire nuts. This is public third-party stuff, and we have more performance testing other than this, backing that up. So it's when you say identified, you can't take it lightly, right?
Right.
Because essentially you're standing behind your product. The product is designed for a certain use, and that's what the identification is all about.
Nice. I had one question asking are any planned updates to Article 250 regarding copper-clad aluminum. I think they did most of that in the 2020, if I'm not mistaken. 250.68, I think, or 62, and I think it's pretty much
Well,
already there.
Article 250 already it allows for copper-clad aluminum.
Yeah, main bonding jumper can be copper-clad aluminum. Equipment grant. Yeah, I think it's pretty much all there. To answer the question in chat. So I can't think of
Mm-hmm.
anything that needs to be updated in Article 250. I
Yeah.
saw somebody online mentioning an inspector mentioning that somebody was trying to use copper-clad steel for a conductor, for an equipment grounding or bonding conductor, and that's not recognized. That's not in the NEC. But
Well, it's in Chapter 7, that's for sure. Um,
oh,
and again,
okay,
it's hard to talk about specific cases, but the copper-clad steel for grounding applications has been around for 170 years,
well
right?
that's what. Yeah, that was the original
Um,
design, right?
yeah, one of the biggest uses for copper-clad steel is grounding of substations,
Mm,
right? Grounding of substations and grounding transformers, which is obviously an outdoor application.
sure.
Um, Wind, rain, the whole 9 yards. Pole line, grounding is part of Copper Weld's business.
Mm-hmm.
So it doesn't appear in Article 250. It certainly
Right.
does not.
Right.
Yeah.
Good deal. Well,
Mhm.
listen, I sure appreciate you taking the time. We've gone just about 2 hours, and I've enjoyed every minute of it personally. I'm kind of a nerd when it comes to this stuff, so I've had a great time, and I think
Yeah.
we've pretty much answered most of the questions that have come along. There
Well,
was one
Ryan,
question. What's the difference between copper-clad aluminum and tinned copper? Do you know if tinned copper
gosh.
is? Do you know anything about it?
Well, tin copper is you put the tin on there for corrosion
Mm-hmm.
purposes. Um, you know, obviously, obviously you can do the same with copper-clad aluminum, but you know, we don't do it, or Copperwell doesn't do that.
Okay.
But if not to say you couldn't, right?
Sure. Sure.
But yeah, tin is designed to prevent corrosion.
Yeah. Okay. And then one more. Is there any difference between the CCA manufactured back in the 70s versus the stuff being made today? For example, a more advanced process, etc. I mean, I'm guessing the aluminum alloy is certainly different.
Right, right. Well, I can't really speak to how it was done back in the 70s, but um, you know, from what I know, it
Yeah.
was back then it was 1350. That's been the preliminary, the primary alloy. Again, that alloy, when cladded,
Mm-hmm.
when you remove that oxide layer, um, does quite well. I mean, we have a lot of legacy installations that do their own talking, right?
Yeah.
Um, so, today's materials made has a 8000 series core and a more thermally stable material.
Right.
Still suffers from the oxide layer, but we remove it, right? We
Absolutely.
remove that oxide layer when we, make copper-clad aluminum. So
Yeah. Perfect. All right. Well, listen, I've really enjoyed it, Peter, and thanks so much for
Ryan,
stopping by,
total
man.
gentleman, thank you very much
Oh,
for
of
allowing
course.
me to speak to your followers
Oh
and
yeah.
audience, and here to serve it. If anybody would like to know more about copper-clad aluminum or copper-clad steel for grounding, our doors are open, and we can we can, you know, explain what we know about these materials.
Yeah, and you know, when you say we, you're of course talking about Copper Weld is the company. And you know, I'm not going to type your email address or your phone number on here, but if you go to Copper Weld and you go to contact us, it's very very easy to get in touch with Peter. So you
Right.
know, yeah, like I say, I don't want to do it because you're going to get robots from every country in the world sending you things, and you don't need that. You know, I get
I got enough robots.
yeah, exactly,
Oh,
exactly. So cool.
yeah,
Everybody's saying thanks, getting good stuff. Firm handshakes to all. It says good. Thank you. Yes.
good. I've
Awesome.
got to rush off to my other commitments, and
Okay.
but I definitely appreciate you guys, and it's unbelievable. We've talked for 2 hours. I'm exhausted.
It's only 2 hours. I talked for eight
How
hours
do
on
you
most of
do
my
this?
classes.
How do you do
I don't
this?
know. I don't know. It's the audience. I
I
don't know
don't
how they
see
do it.
Ryan.
You know. Awesome. Well, thanks again, Peter. I'm gonna shut down the stream and just thank all the viewers and thank you one more time, Peter. So thanks again, and
Okay.
hopefully we'll
Okay.
shake
Very
hands in
good.
Boston next month, if nothing else, and we'll see you over
Oh
there.
yeah, yeah. We'll be there. We'll see you in Boston.
Sounds good.
Gonna be a hoot.
Oh, for sure. It's gonna be something.
See
All
ya.
right. Thanks so
Bye.
much, Peter. All right, buddy.